Hi, everybody, and welcome to this week's homework lab in class. So we're going to be talking about ANOVAs this week. So an analysis variance is basically a test of difference between means of three or more groups. You may remember when we were looking at t-tests, they were looking at 2 scores. Now we're looking at 3 or more scores. Now there's different types of ANOVA, so we're going to be talking about those as well. But imagine that you wanted to look at the study time and say 4 increments of study time for the national counselor exam. You could have 4 hours, 8 hours, or 12 hours, with the dependent variable being the actual score on the test. So these are my independent or grouping variables, and these are my test variables or dependent variables. Another example would be looking at, say, first year, second year, third year doctoral students and their research confidence being the outcome. Another one would be looking at students' knowledge of statistics in week 0, week 4, or week 3. As you can see in all of these examples, there's 3 or more scores that we're comparing in order to test for difference. So we're looking to see if there's a difference between groups. So within these 4 study groups or 3 study groups, 4 hours, 8 hours, and 12, we're trying to see if there's differences within those groups, and also between the groups or within the groups of each one. So at the beginning, if you do a pre and a post, like in a repeated measures ANOVA, is there a difference between the 4-hour group pre an anxiety intervention and post an anxiety intervention, for example? So different flavors of an ANOVA: simple analysis, a variance, also called an ANOVA or a one-way ANOVA. This is where we have one factor or treatment variable that's being explored, and it has more than 2 levels. So like this is a one-way ANOVA right here. We're looking at 4 hours, 8 hours, and 12 hours. Now, we can also have a factorial design, which is used to explain more than one treatment factor. So let's imagine for these study hours, we were looking at students who were in an accredited program versus those who weren't in an accredited program. So we'd have 4 hours, 8 hours, and 12 hours, but for both type of accreditation. That would give us a factorial ANOVA. We also have different designs based on the number of factors we have. In this one, if we had 3 factors, right, and we had the accredited or not accredited, that would be a 3 by 2. So because you have 3 here, there's 3 here, and then 2 by the accredited level. A MANOVA is when you're looking at more than one dependent variable. So if we were going to say, look at their NCE score and maybe their GPA of the overall program, then we'd have 2 outcomes, and that would we would need a MANOVA to analyze that. So we've kind of gone over that. This is the formula for an ANOVA. It looks very simplistic at first, but once you get into it, it's a little bit more complicated. So this is the variance between groups divided by the variance within groups. And as the the F value increases, the more likely something is going on other than chance. So the higher the F value, the better. Now, our hypotheses within ANOVAs are that each of the 3 groups do not equal, that the means are not equal is our alternative. K in this situation, where you see this K, that's the number of independent comparison groups. So here I have some example of some nulls and questions. One way ANOVA is, are there differences by GPA, by grade level, freshmen, sophomore, juniors? And the null for that would be, there are no differences in GPA by grade level, listing those grade levels. A two-way ANOVA would be, are there differences in GPA by grade level, our first variable, and our gender, our second variable. So in this case, I have a 3 by 2, right? So there's 3 levels right here, and then there's 2 levels right here. So that would be a 3 by 2, and that null is there is no difference by GPA by grade level or by male. So this is a little cheat sheet here that I developed that I find really helpful. So it tells me, okay, if I have one independent variable and one dependent variable, it's a one-way ANOVA. If I have 2 or more independent variables and one dependent variable, it's a factorial ANOVA. If I have 1 or 2 independent variables and I have 2 dependent variables, I use a MANOVA. So that was, just a little cheat sheet that I developed for myself that I found really helpful. A couple of caveats. We're also going to be talking about ANCOVAs and MANCOVAs in a later class. those are where you're taking a covariant, a variable that you know is impacting the outcome. So it's something that's moderating your outcome. So for example, in my dissertation, I looked at traditional age African Americans at a historically Black college university versus a predominantly white institution. And I knew that the type of institution was moderating the outcomes. So I used that as a covariant. Real quick note on languaging, a factorial analysis, which we'll be talking about in later class, is not the same as a factorial ANOVA. So make sure you keep those distinct. A factorial analysis does something very different, as you will see when we look at that, versus a factorial ANOVA, which is where you have two or more independent variables and one dependent variable. One of the biggest things about a factorial ANOVA is that we're now getting not only the between group and within group, we're also looking at the interaction of the two independent variables on the outcome. So pretty cool stuff. This is a look at the flowchart about when you would use a simple analysis of variance. If you had, the different types of variables, as I've mentioned already, you would span this out to be, a factorial ANOVA or MANOVA. Now let's work through some examples or talk about different types. So I would have done here is giving you a description of a simple ANOVA. Here's 3 examples: a 2-factor ANOVA, which is a factorial ANOVA, and a 3-factor, or another factorial ANOVA here. So you can look at those examples. I wanted to also show you one that is a bit more complex. This is more of a MANOVA. So here, or this is actually a repeated measures factorial ANOVA. And it's repeated measures because this group A, which are the low-fat male, they're getting this assessment, and this assessment. So we're looking at their, I think, body index scores. And then here you can see for low-fat female, they have the same thing. So they've got the first capture, second capture, third capture for the light smokers that are also in this group. This is year 1. Here's the heavy smokers from this group, year 2, year 3, right? So you're getting 3 measures across these 2 independent variables. Actually, you can think there's 3 variables here, right? The type of body fat, the gender, and whether they smoke or not. And that's how you're breaking up those groups. So this is a repeated measures because I'm testing the same group more than once. Repeated measures factorial because it's got more than 2 independent variables, factorial ANOVA. All right, so practice 1. We're going to look at 3 groups of preschoolers and their language scores. Group 1 spends 5 hours per week in preschool. Group 2 spends 10 hours per week in preschool. And Group 3 spends 20 hours. So I've got my data here, and I'm going to state my null. My null is that there is no difference between the means of these 3 groups, right? So Group 1, Group 2, and Group 3 have no difference. And my research hypothesis is going to be looking at that there is a difference. We don't know where that difference is, but there is a difference. And this is an important component of ANOVAs. The initial step in ANOVAs does not tell us where the difference is. It only tells us there is a difference or is not a difference. So it's really important to understand with ANOVAs, you're going to have 3 distinct steps, and each one of those is dependent on what happens in that first step. So we're going to test for the ANOVA first, or test for the difference. So we're going to use a level 0.05 here. We look at the decision tree. It tells us that because we have 3 groups, we only have 1 outcome. We should be using a simple one-way ANOVA. We're going to be trying to compute the F ratio or F score. And we're going to be looking at between group sum of squares and within group of sum squares and total sum of squares for both the initial decision of significance and also for the eta, which is our effect size for this type of ANOVA. So let's take a look at our data. Now, remember, I always calculate this out by hand just so you can understand how this works, but it may or may not be required as part of an assignment. But it is important to understand kind of how this is working and what's making this up. So when we have ANOVAs, we're going to code by group. So I have these people are coded as 1s, these people are coded as 2, and these people are coded as 3. This is their test score. And this is their test score squared, because I need the sum of x, which is all of their test scores totaled up, and I need the sum of x squared, which is the summation of all these x squared summed up. Same thing here. I'm totaling up x, and this should be an x2, and this should be x2 squared, and this should be x3 squared, and x3, or x3 and x3 squared. And then I bring them over here. And this is kind of a summary that's going to help me solve for my equation. So I always, if you're doing an ANOVA by hand, I really recommend doing it this way, where you have this chart where you calculate your squares and your sum ofs, and then bring them down into this chart. So this is our sum of x1. This is our mean of x1. This is the sum of x1 squared. This is the sum of x1 squared divided by n. All of these are important components of this formula. And then I do the same thing for group 2, for group 3, and then this is all of these guys. So when you see the summation of x, so that means I take this 766 plus this 852 plus this 916, and that gives me this. This, again, the summation of all of the summation of x, which is right here actually. So this one, and this one, divided by n, and this n is all three n's. So this would be 10, 10, and 10, so I'm divided by 30. And then this is the summation of x squared, which is these guys right here. And then, so this one actually is the summation of these, so this number, which is the summation of summation x, which is 2,534, goes right here. I square that, then I divide that by 30. This one is the summation of these guys. And then this one is the summation of these guys. So you can see how this chart can really help you stay organized, because it's really easy to miss a step or lose a step. Then I calculate my between sum squares, which is this formula right here. So I'm just, at this point, just taking this one minus this one. That gives me this number. My within is the summation of x minus n, which is this one right here, minus this one. And then my total sum is this guy minus this guy. Okay, so again, the formulas are laid out, and I just use these charts to help me calculate. Now, my F score is going to be my mean squares of between divided by my mean squares, or mean sum of squares within. So that's going to be this number divided by this number, and that'll give me my F score. So when I calculate that out, I get an F score of 8.799. All right. So this is my sum of squares. This is my mean sum of squares. And then I calculate this out. Okay. So my mean of sum squares is the, I was trying to find that formula. Do I have that formula written out for you guys? I do not. So the mean of sum squares is the degrees of freedom divided by the sum of squares. So I'm going to put that right here. So sum, let me do it this way, equals sum of squares divided by degrees of freedom. Okay, same thing here. So I'm going to divide this by this degree of freedom. So for my between sum, I'm going to take k, which is my number of comparisons, which I have three groups of preschoolers, right? Minus 1 equals 2 for the between group. My within group is how many people are in the group minus the number of groups. So this is 30 in for all three groups, minus the three groups equals 27. My total sum is these two numbers added up together, which will be important later, but not yet. All right, so then we get our mean sum of squares, and then we divide these two to get our F score. Okay, so that is how we get our F score by hand. Then we can, if we want to use the book, if we're not using SPSS, we can go to the back of the book, and we can look up the degrees of freedom under an ANOVA. And I didn't have my book open, but give me a second. I'll pause the video and I'll pull that up for us. Hold on. Okay, so this is, and this may look slightly different depending on which book you're using, but this is the critical value for the analysis of variance for F test. Oh, I keep saying V. All right. So one thing to remember is the number of degrees of freedom for the numerator is k minus 1, right? Our groups minus 1. So in this case, we had three groups, minus 1 is 2. And our degrees for our denominator is the total number of n, which is 30 in this case, minus the total number of groups, which is 2. So that gives us 27. So in this particular case, the first thing we're going to do is we're going to look at our degrees of freedom for our denominator. So that's going to be 27, which is going to be down here. And then our degree, and then we'll find our, this is the 0.05, right? That's the p-value we're using. And then we're going to find the degrees of freedom for the numerator. So in this case, it's 2. So I'm going to come down here, and our critical value is going to be 3. Oh, can't get that up. 3.36. That will be our critical value, which is only if we're not using SPSS, right? We're only doing this if we're not using SPSS. I'm going to find my notes again. There we go. All right, so we've looked that up. And so when you can see 3.35, 3.36 is about the same depending on which book you're looking at. We compare those. Our obtained value was 8.80, and that's well exceeds the 3.35. Since it's more extreme than, since the obtained is more extreme than the critical, we are going to reject it. And our interpretation is that the 3 groups of preschoolers demonstrated a difference in language score. Right? That's so at the 0.05 level. And note, I have F score, I have the test that tells me I did an ANOVA. This is my 2 degrees of freedom. This is my denominator and my numerator. This is my obtained score. And then this is my p-value of less than 0.05. Okay. Sometimes people ask, why can't I just run multiple t-tests? Well, if you're running on the same data, every time you run on that data, you have to actually increase the type 1 variable. So in this particular case, we would have to put a 3 here because that's our k, right? So 1 minus 1 minus the alpha is 3. So in this particular case, that's going to give us a 14% significance level, which we know far exceeds the 0.05, so that's unacceptable. So therefore, we can't run multiple t-tests on our data. Now, if we run an f-test for an ANOVA and we find that our findings are significant, which we just did, then the next thing we can run is effect size. And the effect size of a simple one-way ANOVA is an eta squared, which is the between group sum of squares divided by the total sum of squares. And this is our little cheat sheet for interpreting whether it's a small, medium, or large, because remember, we report our effect size as small, medium, or large. So in this particular case, we plug in those numbers from that beautiful chart that we created up above, and it gives us an eta of 0.39. When I look at this chart, it tells me that is a large effect. So my decision is, according to the small, medium, large guidelines for eta squared, 0.39 is a large effect. Now, because my findings were significant, the next thing I can do is run a post hoc. A post hoc is going to tell me where the differences are in the ANOVA. In order to do that, I'm going to actually use SPSS. Unfortunately, I do not have my SPSS on the computer that I have with me. So I am going to have to trust that you guys will run this on SPSS, and I'll show you what the scores look like. But I have your steps here, and this is the data set right here that you should be able to link to. So let's scroll on down. This tells you what we're going to find, but here's what it looks like. We get our descriptives, which describe each of the groups. So 5-hour, 10-hour, 12-hour, right? Mean, standard deviation, our confidence interval, all of that. Minimum, maximum, very helpful for testing and make sure that there's nothing weird about our data and it's out of bounds. Here's our between group, our within group, and our total group. Numbers should look very similar to what we just calculated by hand. Here's our mean squares. We're dividing that by we divide these two to get our F score, which is significant at the 0.001 level. So this is how I would write that. And this would be the 3 groups of preschoolers demonstrated differences in language scores. This is my type of test. These are my degrees of freedom. This is my obtained score. This is the significance level. And then it's two-tailed because my null was there's no difference, right? And this just tells you how to write out. This is the words, and you replace them with the different numbers. Okay, so now let's look at post hoc. Now, for this particular example, we're going to do a Bonaferroni, but there's different ones. There's Tukey, there's LSD. You can choose any of them, but for this particular one, I'm going to run a Bonaferroni. You'll see that you don't really get much difference if you run them multiple ones. I will say that I find it helpful to just click to run the post hoc when I run my ANOVA. If my ANOVA is not significant, I just don't look at the post hoc. right? Because if the ANOVA is not significant, there's no reason to look at the post hoc because none of the findings are going to be significant. But in this case, we did have a significant finding. So let's see how we interpret this chart. So this is what a multiple comparisons, it's also called a pairwise comparison, looks like. So here it's comparing the 5-hour group to the 10-hour group. There's a mean difference of -0 or -8.6. And I can see here that that is not a significant finding, right? Because that's greater than 0.05. So I'm not even going to worry about that one. This is the 5-hour to the 20-hour though. And you see that little asterisk? Remember I told you that asterisk means that it is significant at the 0.05 level. And sure enough, when I come here, it's significant at the 0.001 level. In some articles, you'll see that if it's significant at the 0.001 level, they'll actually put 2 asterisks. All right, and then we can continue to look. We know this one's not significant because this is just the mirror image of this one. But what about the 10 to 20 hours? Is that one significant? Nope. Here again, this is the 20 to 5, which is the same one we looked at here. So that's a significant. So while the whole ANOVA was significant for having a difference, the truth of the matter was only the 5 hours to 20 hours had a significant finding, which is kind of interesting, right? So now you know how to do the post hoc. Now let's talk about how to make this graphs. How do we see this graphically, right? And one of the ways we demonstrate or we create graphs for ANOVAs is through error bar graphs. And so I've given you the instructions for how to create an error bar graph right here. It goes through all the steps for this particular example that we just did. And you'd get a graph that looks something like this. This is the 5-hour group, this is the 10-hour group, and this is the 20-hour group. And you can visually see the difference. And this is, of course, based off confidence interval. So I'm 95% confident that my true mean falls between this point to this point, and this is the mean I found. I'm saying I'm confident that the true mean is between this and this with the mean I found here, the obtained mean. This is the observed mean, right? From here to here. All right. And then if you want to learn more about how to do bar graphs, I've given you a couple of additional resources here. Now let's go on and do another data set. So this time we're going to be looking at swimmers who practice less than 15 hours, 15 to 25 hours, and greater than 25 hours. And they're doing the 100-yard style race. Now our factor or grouping or independent variable is the practice time. Our outcome testing or dependent variable is the time that they actually swim a freestyle. So here's your data set. You're going to run it through Analyze, Compare Means One-Way ANOVA. Tells you how and where to put your factors, and it's going to give us these results. So you can see here's all of my descriptive data for the people who practice less than 15. Here's all the data for people who practice 15 to 25, and here's people who practice more than 25. Then I have my source table, which is what this is called, and that's going to give me my between group, within group, and total group. Boom, boom, boom. My degrees of freedom. Boom, boom, boom. If I look here, I had a total of 36, right? That was my total N. So this degree of freedom is K minus 1, which is 3 groups, right? 3 practice groups minus 1. And then this one is N minus K, so it's 36 minus 3. And then this 35 is these two added together. I get my mean squares, gives me a F value of 0.160, and it is not significant. So because I have found a not significant finding in my ANOVA, I am not going to calculate the eta square, and I am not going to calculate post hoc because I don't need those because they're not going to be significant. You've got to have this step first before you can proceed. All right, so this is what it looks like though if you were to run it, and as you can see, none of these are significant, right? They're not significant. So even if I had run it, it wouldn't have come through. But here's how I would interpret this. The means for the 3 groups are 58.05 seconds, 57.96 seconds, 59.03 seconds, with a probability of this F value being F with degrees of freedom 2 and 33 equals 0.160 at a p-value of 0.853 occurring by chance. It's far above what we would expect due to the treatment. Our conclusion, the number of hours of practice makes no difference in how fast you swim. Now, do I think that's really true? No, I don't actually. I think the more hours you practice probably does. One of the things that I know immediately though is that with a n of 36 across these three groups, I've already violated one of the assumptions of parametric statistics, and I'm not going to be able to calculate a real true finding here because I can't assure myself that I have a normal bell-shaped curve. I really would need at least 30, ideally at least 120, in order to be able to really feel confident that this was representing a normal bell-shaped curve based on the central limit theorem. So therefore, I am not surprised by these findings because my sample size was just too small. All right, let's look at another one. Let's look at stress among three groups of employees. Employees who work morning and day shifts, employees who work day and evening shift, employees who work the night shift. So my hypothesis is, my null hypothesis, there's no difference in the amount of stress between these groups. Factor IV, outcome. Here's your data set. Here's how you put it in. And we're going to go ahead and click on the post hoc just in case we have a significant finding. These are my descriptives. It tells you a little bit about each one. Now, again, I'm already aware I'm violating the assumptions of an ANOVA, but we're just for practice going to go ahead and continue. Have my between group, my degrees of freedom, my F score, and my significance. Okay, this is significant. Now, this is my Bonaferroni, and my is called a post hoc, and I can see this one is significant. The 4 to 8, or so the swing shift to the day shift is significant. The midnight shift to the swing shift is significant. All of these are significant, actually. So I can see, and you can see that these are just mirror images of each other here. All right, so I only have to report one version of them. And here's the significance levels for those. All right, so what's a critical value? It's not needed when we run in SPSS, but if we're interested, we can use the appendix in the back of the book and we can find that out. But we don't need to find the critical value if we're using SPSS because it has calculated the actual significance level for us. All right, we're not guessing. Right, so here's how I would report it. Okay, now, is this result more significant, because it's at the 0.001 level? No, it is just significant at that level. It is not more significant, and that is so important to remember. The least stress group, if I look up here, I can see that the group of the the day shift group here, you can see the amount of stress they have versus the amount of stress this group has is this is the highest number, but because it's a negative, it means this group has more stress than this group, right? Because this group would have to have a much lower stress. If you're subtracting lower stress from a higher stress, you're going to get a negative. So this is the least stressed group. Okay? And then here's how I do effect size. I just take those between of groups and total sum of groups, which are in my thing right here. And I calculate my eta and I interpret it this way. Okay, so in this particular case, I have a large effect size. Let's look at one more simple analysis. So this is Noodles and Co. One of the things I want you to note, though, and I told you guys that I was going to be doing this is a reverse scale. So this one's going to be a little harder to interpret because 1 is the most pleasing, where we tend to think about scales usually being the higher number is better. In this case, the lower number is going to be better. So we're going to go look up this data set, which I actually have linked here. Sorry, I didn't link it there too. And we're going to calculate that, okay? So this is how to do it. And I already have the answer up here, but we're going to continue to, we're just going to run the post hoc here. So we run you can actually practice running the ANOVA. And when you do, you get the results that look like this. So it's a significant finding. But let's look at the post hoc. How do we know which noodle is the most appealing? Sorry for the yawn. So in this particular one, remember a 1 is better than a 5. So in this case, I'm going to be looking for a lower finding here. So in this particular one, this one, while low, right, the difference is low, it's not significant. So I'm not even going to look at it. But this one is significant. So is this one. Yes. So in this particular case, as you can see, remembering that 1 is the lower number, this is going to be the most pleasing. So in this case, because this is positive, right? 1 being that's going to be thin. So the thin in this case, because this is negative, I know that's lower than a positive. So the thin is going to be the most preferred of the noodles because I would have to have a lower number here to be able to get a negative here. So this number would have to be bigger than this number. This number is bigger than this number to get a positive. So remembering that the lower the number, the more pleasing it is in this particular case. So there is a significant difference. And with the post hoc, I find that it has the lowest pleasing score at 1.80, which actually shows up in when I do the full results. But unfortunately, I don't have the SPSS full results here, but you'll just have to trust me on that. And the pairings here also tell us that. I can do an effect size for this particular one where I take my between and my sum of squares, gives me an effect size, an eta square of 0.40, which is again a large effect size. Here's the way I would report all of my results together. And this should actually be a 1, not a 0. So it should look like that, okay? Because we never have a 0 finding there. So I hope that this part has been super helpful in helping you identify how to interpret and understand the different steps of an ANOVA. All right, so why is it only appropriate to do post hoc analysis if the F ratio is significant? Well, there's only differences if you find that there are differences. So there's no need to do a post hoc unless you find a significant finding. Now, remember that Factorial Anova is another form of ANOVA. We have two types, two-factor without replication and two-factor with replication. This is also called a repeated measure. So basically, I'm testing the same people more than once. Remember, we had something very similar when we did the dependent t-test. So think of this as kind of your dependent ANOVA, and this is your independent ANOVA. And this one, we're testing them multiple times, and we have multiple groups that are being tested multiple times. So an example would be something like this. I have treatment and severity, and under the treatment, I have 3 types of drugs that they could get, and I have the type of severity of illness. This is an example of how I might write my template for writing research question for Factorial Anova. And then I have the hypotheses here as well. This is your null, this is your alternative. Now, there's lots of things we can do with this. We can talk about the between group differences, which is called a main effect, and then a main effect for the illness. And then we have what's called an interaction effect, where we look at the interaction between the drug treatment and the severity of illness. So that's when I'm looking at this, like a cross, right? I'm looking at 2. So I'm looking at comparing the different effects between the two variables. So main and interaction effects are important to distinguish. So if I have this 3/2 factorial ANOVA, then I'm going to have 2 main effects and I'll have 1 interaction effect. All right. And then just like with our other things, K is our number of comparisons, N minus K is our total observations minus our comparisons. I have another data set for you to play with. This time we're looking at levels of stress and gender and the impact it has on caffeine consumption. And so I have stress and I have gender. Gender has 2 levels and stress has 3 levels. So this is a 3/2. You always do this level first. So 3/2. And here's our null. There's actually 3 null hypotheses. So there's no difference in stress, there's no difference in gender, and there's no difference in stress and gender between the two. All right, and then there's my hypotheses for the alternative. Going to set it at a 0.05 level, just like everything else. We'll go to the decision tree. We decide that our appropriate test is a Factorial Anova. And for SPSS, we're going to use these steps in order to punch it in. Notice we're using a different part of the system now. Analyze general linear model univariate. We're going to put in caffeine consumption in our dependent, gender is going to be in our fixed factor, and stress is in our random factor, right? Fixed factor and random factor. We're going to look at our descriptive stats and click SPSS, and this is what we're going to get. This tells us a little bit of data about our 2 independent variables. Here we have our independent variables connected. So male low stress, male moderate stress, male high stress. This is the interaction and the descriptive statistics related to that. Now this reads a little differently. Now we have a gender, which is a main effect, stress main effect, and this is how your interaction effects are written out. They're gender times stress. And so here we have that our significance, our F stat is 7.03, and it is significant at the 0.042, so that's less than 0.05. Stress, however, is not significant, nor is the interaction of stress. So the only one that's significant is gender. And so we're going to scroll on down. I've got some explanation of that. Tells you how to write out each one. For gender, we would have this answer. For stress, we would have this answer. And for our total interaction, we'd have this answer. So I have some questions here. It says, is there a difference between the levels of caffeine consumption among the stress? No, it's insignificant or not significant. And this is how I write my results. If it is significant, like with gender, this is how I write my results. Is there an interaction? Nope, there are no significant interactions. I also have a line chart that I can create here that you can create through the legacy dialogues and graphs. Choose line chart and put in both of your findings, and you can get this. Okay, I would drag stress to be my x-axis, and then I would set gender as my second one. Okay, and that is my review of ANOVAs. I hope that this has been helpful. Let me know if you have any questions or concerns. I'm sorry that I couldn't be live with you to do this, but I will post this material and welcome questions through text or in the classroom. All right, have a wonderful day.